Today's discussion is on the analysis of forces on balloon. This is basically spinning balloon. Let us take an analogy first and try to understand how a balloon is going to work and what are the various forces which will be acting on it. So, we start with a system that consists of a rotating mass and which is tied by a string. We can see the diagram that the mass is m and there is a string, the mass is rotating following a circular path. The string is passing through guides as shown here. This is the guide, this is another guide, and there is a resistance to the string, and because of the resistance the tension which is acting on it is T, and the string is also moving with a velocity v. The string is free to move along its length with a velocity v. Now, this is quite similar to the facts that we see in a spinning balloon as well. Now, here this is the system we try to understand first, then the rate of doing work in this case is going to be tension into the velocity with which the string is running, that is T v is the rate of doing work, all right. And the other equation which is the centrifugal or centripetal force that will be acting on the mass, and that is 2 T is going to be m r omega square, where omega is the rotational speed of the mass in terms of radian per second. So, and omega is related to the rotational speed in terms of revolution per second, that is omega is 2 pi n. So, in this particular case these two equations needs to be satisfied. Now, we will discuss about two different conditions. Condition number 1, that is no work is being done. So, there is no work being done, that means the right hand side of the equation 1 is going to be 0 if I am not doing any work. So, if it is 0, when it can be 0? When V is 0. So, if string is fixed suppose and therefore, V is 0, in that case T may have any value and equation 2 will still be satisfied. Equation 2 is 2 T is m r omega square. So, this equation will be satisfied even if V is 0 when I am not doing any work. The other situation is string is moving, but there is no resistance to the movement. So, if there is no resistance to movement, that basically means T is going to be 0, that means there is no tension in the yarn, because there is no resistance to the flow of the yarn. So, from equation 2 we can now write that it is T is 0, that means m r omega square, this is going to be 0 also. Obviously, m cannot be 0, m is the mass of the small block that we have considered here. So, now there are two possibilities, that is either r is 0 or omega is 0. that is the mass is either on the axis of the rotation when r is 0 or it does not rotate at all, that is omega is 0. So, this could be the situations if we are not doing any work, that is either that means V is 0 or T is 0. The second condition is the work is being done at a finite rate. In that case, the tension will be determined by the equation 1. If we are doing the work, some work is being done, that means T n to V has got certain value, and therefore, if V is known, then we will be able to know what is going to be T, that is equation 1 is being satisfied. And from equation 2, we can find out for a given value of omega what is going to be the value of r. That is, if I doing work at a certain rate, then there will be some value of T, that is some tension will be there in the string, and that tension 2 T will be equal to m r omega square. So, once 2 T is the T value is known from the equation 1, then we can say that there will be going to be some definite value of r or omega. That is, for a given omega, we can find what is the value of r, or if we assume r, then we can find out what is going to be the value of omega. So, system can be in equilibrium only for one length of the string. This particular situation has lot of similarity with the spinning balloon. The balloon tension is therefore is determined by the energy consideration. So, as work is being done, then only there will be some tension, and for a given value of tension and omega, there is going to be certain radius r. So, once tension is fixed, the yarn length in the balloon and its shape are fixed such that the tension provides the necessary centripetal force on each element of the yarn. If the source of tension is the friction between ring and traveller and also the air drag on the balloon. So, these two are the source of tension in the yarn, because the yarn has to pull the traveller around the ring and there is enough friction between ring and traveller. So, that is a source of tension, and the other source is the air drag on the balloon, because the yarn is rotating in the medium of air at a very high velocity. So, there is going to be some drag, and the air drag is also responsible for some tension. So, you have to remember the source of tension is the friction between ring and traveller and also the air drag. Centrifugal force is not really the cause of tension. Now, from there we will first discuss about the propagation of small transverse wave, because a spinning balloon, we will see we can consider it to be a kind of wave. So, those who have studied wave and still remembers in your class 2, these are the very basics of the wave propagation. So, let us consider propagation of transverse vibration along a straight string. So, as shown in the diagram, lambda is the wavelength and f is the vibration frequency. Each portion of the string describes a wave in the direction perpendicular to the direction of propagation of wave, and it follows a SHM of frequency f and amplitude equals to the amplitude of the wave. Velocity of propagation of transverse wave has been shown to be root over T0 by m. Velocity of propagation c is root over T0 by m. So, what is T0? T0 is this tension in the string and m is the mass of string in terms of gram per centimeter. So, that will give you the velocity of propagation of the wave. The unit is going to be centimeter per second. Now, for a typical wave, the velocity of propagation of the wave is also written as c is equal to lambda into f, where lambda is the amplitude and f is the frequency. Therefore, we can write lambda is going to be c by f, where c value if we take from equation 3 and put it, then we get lambda is going to be 1 upon f root over T 0 by m. So, that gives you wavelength of the wave. So, wavelength of the wave is a function of the frequency, the tension and the mass per unit length of the yarn. Now, here we are showing the wave propagation, another diagram. Now, when both the ends of the string are fixed, the wave is reflected from both ends and the resultant motion is determined by superposition of direct and reflected waves. Like here we are showing it. The conditions for stationary wave pattern with number of loops, the distance between adjacent nodes. So, here is a node, there is another node, and this is L is going to be multiple of lambda by 2. So, displacement of any point on the string varies sinusoidally with time, and amplitude varies also sinusoidally with distance from the fixed end, and points where the displacement is 0 are called nodes. So, these are therefore are called nodes. The lambda is shown is complete wavelength and the distance between the nodes becomes lambda by 2 is half wavelength. So, these are the basics of wave propagation which we can find out in any standard textbooks on of physics, but this is what is going to be used in our case also. Another aspect is about the waves is the circularly polarized vibrations. What we have discussed is plane polarized vibration, that is it is the string is vibrating in one plane. Now, that could be situation where something may vibrate in two mutually perpendicular plane also. So, if the string is made to vibrate with same frequency, same amplitude and phase difference of 90 degree in two mutually perpendicular plane, then each point on the string will describe a circle about its equilibrium positions, and this is what is known as circularly polarized vibrations. Each point, that is if the string is made to vibrate in two mutually perpendicular plane, you have to remember, and with same frequency and same amplitude and phase difference of 90 degree. In that case, any point on the string is going to follow a circle as shown in this diagram, and this is what is known as circularly polarized vibration. So, a balloon is also following a particular element on the balloon is following this kind of path. So, therefore, balloon is considered as circularly polarized vibration of a string. From there, we go to the next slide, and here what I am trying to discuss, the rule which is valid for polarized vibration will also be applicable to circularly polarized vibration as well, and therefore, we can write in this situation also lambda is going to follow the same rule, that is wavelength will be 1 upon f root over T 0 by m, and f is going to be omega by 2 pi. So, if I replace f by omega is going to be 2 pi by omega. So, that is what is going to be the lambda, and we say lambda value is again connected to the omega rotational speed the tension which is there and the mass per unit length of the yarn. The distance between the nodes, here it is being shown that the node is somewhere here. So, this distance between the two nodes, that is L, will be lambda by 2, it is half wavelength, and therefore, it is going to be pi by omega, because 2 pi is there. So, 2 and 2 will cancel. So, we will be left out with pi by omega root over 20 by m. This quantity omega root over T 0 by m, we replace it by p. So, p is root over T 0 by m omega square. If I take omega under the square root, then omega changes to omega square, and therefore, p becomes root over T 0 by m omega square. And we write that the distance between the nodes, that is from here to there, is always going to be pi p, where the value of p depends upon the tension, mass per unit length of the yarn, and omega, that is the rotational speed in terms of radian per second. So, when the amplitude of vibration is small, the balloon profile is a close approximation to sine curve of half wavelength, that is pi p. It is a close approximation to a portion of the sine curve of half length, that is pi p. So, you see it here in the diagram, node to node distance L is going to be pi p, but if this blue circle indicates the location of the ring. So, the ring is here, then the distance from the top node to the ring is h, that is the balloon length or balloon height. So, h is balloon height and L is the distance between the two nodes. What we have to always make is that this node, the bottom node, should not be generated above the ring, or we can say, so that h is not less than L. If h happens to be less than L due to any reason, then the yarn is going to touch the surface of the bobbin, and that may lead to basically finally breakage. So, a stable balloon basically means that the height should be such that it is less than node to node distance, and what that distance is not fixed, that distance L is a depends upon a value p, where p in turn depends upon tension, value of m, count of yarn, in a way you can say mass per unit length, and also the speed with which the element of yarn is rotating. Now, from here we can make some useful remark. First, the height of the balloon cannot exceed L, that is what we have already discussed, without the formation of a node, and we do not want nodes to be formed, otherwise spinning will not be possible. If the balloon height is increased considerably, then multiple nodes may form and we will not be able to spin the yarn, because if node gets formed between ring and the, let us say this is the lappet guide locations, then same problem will be there, the yarn is going to contact the surface of the bobbin, is going to be abraded and yarn is going to break. So, you have to make sure that too much increase in balloon height under given circumstances may not be possible, but the challenge is that how to make a big balloon, a lengthy balloon, so that we can have a long package, and the package is big, we will be able to wind more yarn. So, from the point of view of increasing the content of yarn in the package, we need to form a longer balloon. The package always resides within the balloon. So, for a given value of ring radius, balloon height, there is a limiting value of p for which a balloon without a node can be formed. So, there is a limiting value of p, and this is what is most important. We will see to it. The limiting value of p decreases as r by h increases. What is r? R is the radius of the ring. R by h increases basically means what? That means the value of p will decrease as r by h increase, the ratio of ring radius to balloon height. The maximum theoretical value of h by p is how much? H by p maximum is actually pi, because L is equal to pi p. The distance between two nodes is pi p, and lambda or your h will be cannot exceed the distance between two nodes, and hence the h by p maximum value of this can only be pi. If we exceed this, a node is going to be formed and we will not be able to spin the yarn. So, h by p, this ratio, the maximum value of this ratio can be at the most pi, and ideally it should be always less than pi. So, for stable balloon, therefore, h by p should be less than pi, and in a way that basically means p is going to be h by pi. We are writing the same thing, and if I replace p by root over T 0 by omega square m, then we can write that for a stable balloon this condition has to be met, that is root over T 0 by omega square m should be always greater than h by pi. Unless this condition 7 is met, a stable balloon cannot be formed, and stable balloon basically means that we will be going towards balloon collapse, and balloon collapsing means that a node is about to be formed, and a node formation basically means that spinning will be impossible. Okay, from there you go to the next slide. Now, for a given value of p, ring radius r and balloon height h, the length of the yarn in the balloon always adjusts itself, so that a stable balloon is always formed. Fortunately, what happens that when you spin the yarn and there is a possibility of self adjustment of the yarn length within the balloon. So, what happens that balloon will automatically adjust itself in terms of its shape, so that or length, so that the right tension is generated and we get the right value of p, so that the balloon does not collapse easily. So, h by p max for different values of r by h has been found out, and this table gives this data that for different values of r by h, r indicates the ring radius and h indicates the balloon height. So, r by h value could be 0. In that case, h by p max is going to be value of pi, which is 3.14. When r by h is 0.05, the maximum value of h by p max is going to be 2.65. So, that means in that case we have to have h by p max value to be on the safe side, should be less than 2.6.5. This is the maximum value, that is, this is the threshold value. If we cross this, then the node is going to be formed. So, these are different values of r by h. Typical values of r by h in most of the spinning situation is between 0.1 to 0.2. If we see in a in a machine that R and H combination, if we take the ratio, we will find that in most of this machine it will be somewhere 0.1, 0.2, somewhere in between these values will come. That means, suppose we will take an example and show it also. So, these are the different values of H by P max. These are threshold values that we should not cross this value. In fact, it is better if we keep the H by P max value less than this. So, that a stable balloon is formed and we can spin the yarn without formation of node, that is we can avoid balloon collapse. The role of air drag also we have to understand that air resistance help to stabilize the balloon shape and yarn tension against any minor change, any minor fluctuation of say yarn count or speed, because the traveler lags is continually changing, depending upon where I am winding. So, that means even though spindle speed is fixed, the balloon speed is not fixed. Balloon speed changes a bit because traveler speed is different. So, spindle speed is constant, but the balloon speed is not. So, that is a change. Similarly, sometimes a yarn may come, a segment of yarn which could be thinner or which could be thicker also. So, these are the various factors which the system will face when the spinning is going on. So, air resistance in a way help to stabilize the balloon shape and yarn tension against any these such kind of minor changes. So, with example, let us say suppose a yarn count m decreases due to a thin region which is passing through it, not thin place means not a short thin place of 1 inch or so, let us say long thin region is passing. So, there is sudden change in locus, the mass per unit length of the yarn. So, what is going to happen? It will cause P to increase. If m decreases here, then P is going to increase because m is in the denominator. Hence, R by P and H by P both will decrease because P is going to increase, R value is fixed and H value is also fixed. So, if P is going to increase, both of them are going to decrease. Now, if so, what will happen? It will reduce the maximum balloon diameter and reduce balloon size will in turn reduce air drag, and thus there will be less tension in the yarn. The drag when the balloon is rotating in the medium of air, the total drag depends the length of yarn which is there in the balloon. If the balloon is larger in size in terms of diameter, that means basically means more yarn is there from the ring to the lappet, or if I go for a longer balloon length, then also there will be more yarn in between the lappet guide and the ring. So, the length of yarn that exists in between the lappet guide and the ring, that decides the magnitude of the air drag. So, therefore, the size reduces, the air drag will also reduce, and air drag reduce, the tension T 0 is going to reduce. And reduced tension it basically means reduction in P. So, we started with increase with m decreasing, and what we finally see the effect of this is to decrease tension also as a result of this, and as a result P is also going to now decrease. Earlier was if we go only by m considering T is not changing, so decrease in m means more P, but you see that because m is ultimately affecting T also, the net effect is P will also reduce, and therefore, there is a possibility of reduction. So, there is a possibility of increase in P because m going down, at the same time there is a possibility of P to decrease because T0 is going down. So, these two will cancel each other to some extent, and therefore, P may not change substantially, and that basically means that that is the way the system will self adjust and avoid a collapsing tendency. So, once we start the spinning operation and we see that it is working nicely, that we have a stable balloon, then minor variation due to any reason is not really going to create much problem. So, a slight change in count has much smaller effect on balloon shape than it would have in the absence of air drag. So, therefore, why it is happening? Why T0 increased or decreased? Because change in balloon size, that is the reason. So, that is why there is a self adjusting effect because of the air drag. That is the advantage we have having the air around us or around the machine. So, air drag actually helps more for the finer yarn at a lower specific tension and limits the maximum balloon diameter. So, the air drag actually helps more, and in the case of very fine yarn production, where we can spin the yarn at a lower specific tension. Specific tension basically means that if we tension divided by the mass per unit length, that is what is specific tension. So, that value, that is the minimum tension that you need to produce a yarn without encountering the possibility of balloon collapse, that tension that we need. If we go for different counts and we try to find out the specific tension that is required, then you will see that in the case of finer yarn, we will be able to spin it at lower specific tensions in a way that helps, because finer yarns are also weaker. Now, we will discuss an example. Suppose a 20 Tex yarn is being spun at a spindle speed of 1500 radian per second by using a 25 millimeter ring. The maximum balloon height is 250 mm. What minimum tension is required to spin the yarn successfully? So, we are not discussing about the maximum tension, we are discussing about the minimum tension that we need to avoid balloon collapse. If we go beyond that tension, obviously the possibilities of collapsing will be less and less, but we have to also see how far we can go beyond the threshold value of the tension, because the more tension we have in the yarn, the more end breakage also we can encounter, because due to some other reasons. So, here it is all about the tension required to spin successfully by avoiding balloon collapse. The solution is, we find out what is R by H value in this case. So, R is 25 mm, H is 250 mm. So, R by H is 0.1 in this case. From the previous table, we have to find out what should be the HP max for R by H 0.1, and if we look back that table, we will get a figure 2.44. So, this is the threshold value of H by P max, that is that H by P, this ratio should be less than equal to 2.44. It should not cross 2.44, it should be less, or maximum is 2.44. From there, we know that for stable balloon, we have discussed it earlier, that this ratio has to be greater than H by now 2.44. From there, we can find out what is the value of T. T should be greater than m omega squared H by 2.44 whole square, and if I put the values of m omega here, then because 20 takes yarn. So, 20 10 to the power minus 6, 20 takes means 20 milligram per meter. So, that we have to convert it into kg. So, 20 to the power minus 6. Omega is 1500. So, 1500 square, and then h in terms of meter is going to 0.25 and then 2.44. If we do this, we arrive at this figure 0.472 Newton. In terms of millinewton, it will be 472 centinewton, 47.2 gram force, 46. That means, in this situation we need tension to be generated which should be at least 46 gram or 47 centinewton to be able to spin the yarn successfully. It should not be less than this. I can keep it 50, it is still better, or 55, it is still better, but as I said, that does not mean the more value I keep, the better it is, because if it is too high tension in the yarn, then the yarn also might start breaking, because the yarn, some part of the yarn may be weaker than the spinning tension. So, balloon collapse basically means, as I said, formation of a node like this. Balloon collapse leads to node formation, which causes yarn to abrade against the bobbin surface and leads to end break. To avoid the node formation, R by P and H by P must be small. That means, P value should be high, automatically means for a given value of R and H. Thus, for a given yarn count, either, so P is this. If I want to keep P high, the options are to play with T and omega. Now, M is fixed for a given yarn count, so M cannot be changed. So, the only option is T and omega. So, if we go for high T 0 and omega is small, both will be undesirable. By keeping omega small, I can make P high, but if I do so, what is going to my harm? What is the answer? Why I am saying both are undesirable? We have already discussed about T. Higher T means more possibilities of break. So, therefore, T 0 should not be very high, but if I keep omega low, then also P will increase. But why we are writing that this is undesirable? What could be the reason? The answer is simple, not difficult, it is just not coming to the mind. Less omega means less production. Omega means connected to spindle speed. So, spindle speed if we keep low, productivity will be low. So, therefore, both are undesirable from omega low, from commercial aspect, both are basically commercial. If the end breaks also too much because of T 0 being large, that also means my efficiency will go down. So, node formation occurs gradually when H is increased or traveler weight is reduced. Maximum collapsing possibility will be when winding at the maximum bobbin diameter and with the longest balloon, that is when H is maximum and P is minimum, because when I am going winding at the maximum diameter of the bobbin, that is near the shoulder of the chase, there the winding tension is low, and because of this T 0 also will be low. So, T 0 being low, P will reduce. That is why I am saying that P is going to be minimum at that case. So, that time P is small and H is very high. So, P is small, H is quite high, H by P ratio is going to exceed that threshold limit, and therefore, we may encounter node formation, like in between if a node gets formed and the spindle is resting here. So, it will come into contact with the bobbin surface and the yarn is going to abrade and is going to break. So, to avoid this balloon collapse or to be able to increase the length of the bobbin, balloon control ring is one solution. That is why balloon control rings are there it will reduce the maximum balloon radius and therefore, it will reduce the air drag. The part of the tension is coming from air drag. So, it is going to reduce the air drag also by reducing the balloon radius. Each section of the smaller balloon, actually here these two dots that you see, the blue, this is basically the control ring, cross sections of the control ring, which is a balloon control ring. So, it basically forming two balloons. So, by having a control ring, we are actually forming two sub balloons, a bigger balloon. If we do not have a control ring, by having a control ring, we are actually making two small balloons. Control ring must have the same radius as the ring and can't be smaller, since the package will not pass through it. So, we have to remember, because the package which is placed it goes beyond the control ring. So, if I have a smaller diameter of the control ring than the ring, then the size of the package will be restricted. So, it should not be less than the control ring size. If it is larger, its effectiveness in increasing the height of the single balloon span and the same tension will be reduced, because then the balloon is not going to be suppressed much. So, that is also the if we make it too large, that is a problem. So, generally it is close or equal to the diameter of the ring. So, basically by having a control ring, we are forming two balloons, and each section of the smaller balloon has a small value of h. Now, this balloon has a h which is a to b, and thus it will reduce the ratio h by p. For if the p remains fixed, let us say, now I have one balloon converted to two balloons. So, total h has decreased by h by 2, it has become. So, now h by p value is going to also decrease, and therefore, the ratio of h by p is not going to exceed the threshold critical value, and hence we will be able to spin the yarn, and we can have a longer spindle or longer, so the bobbin we can keep it and make a larger package. Total height of the balloon, if I look at this diagram, it is very easy to understand. The total height is AB plus BE, AB plus BE minus BC, because within BE, BC is also coming. So, it is AB plus BE minus BC, and if we know that BE and AB are same, AB and BE are same, they are basically both the balloons are of equal size. So, they will be same in terms of length. So, BE can be replaced by AB. So, AB plus AB, it becomes 2 AB, and BC is AC minus AB. You see, BC is what? A to C minus A to B. So, it becomes finally 3 AB minus AC. That is going to be the total height of the balloon. Now, we go to the tension part in the balloon. Here a diagram is shown on the right hand side. This line indicates the way the yarn is lying. Assume that it is lying in a plane, though in the actual case the balloon yarn never lies in a plane. It follows a 3D curve, and that is because of the air drag. Though on this diagram we are showing it as if it is in xy plane, but in actual case the yarn is inclined, and therefore, it is never is in one single plane. But for the time being, for this analysis, assuming that the yarn path lies in a plane and it rotates around the balloon axis at a constant speed, and that speed is omega. The tension at any point in the yarn on the balloon has been shown to be, there is a lengthy derivations which I am avoiding, but we are directly lifting from a standard textbook that the tension at any point on the yarn in the balloon can be written as T0 minus half m omega square r square, where r is the, suppose in this case this is the element of yarn shown by this black rectangle. So, this is at a distance r from the axis of the spindle, and T0 is the tension at the lappet guide. Here tension is, m is mass per unit length of the yarn, and omega is the rotational speed, and it has been shown that T is going to be, tension here is going to be how much? T0 minus half m omega square r square. That means, tension at this point, lappet guide point, is more than the tension here, tension there, because T equal to T0 minus. So, we have to subtract this value. Therefore, whatever is the tension here is much more than what the tension is there on the yarn balloon at different points. So, r is the location of the element from the axis. So, if I go to different values, if I go to different points on the balloon curve, we can say that the same yarn at different locations will have different level of tension, because r is different. Okay. From there, the balloon profile is such that on any element of yarn, the vertical component of tension is always constant. The profile, this also can be proved, but we are not going into that details now. You just have to remember that vertical component of tension, that is T cos theta, is always constant. On this kind of curve, here the T cos theta is the vertical component, is always constant, and T sin theta is this component, which is going to balance the m r omega square. T sin theta provides the necessary centripetal force, and that is why it takes a beautiful shape. The shape is such that vertical component of tension is at any point on the balloon will be constant, and the horizontal component of tension will provide the necessary centripetal force, which will balance the m r omega square, the centrifugal force which is acting on the element of yarn. Now, we are going to discuss spinning and winding tensions. So, look at the diagram on the right hand side. This is our spinning zone, this is the balloon zone. Here the tension between the yarn that lies in between the front roller and the lappet is T s. The tension at the lappet guide is T0, because yarn is now deflecting, and then that is the balloon. On the balloon at the traveler point, the tension is T r and the winding tension is T w. This angle as shown it here is theta, and this angle as shown it here is beta. Now, the relationship between T0 and Ts, T0 is Ts e to the power mu 1 into theta, where mu 1 is the coefficient of friction between the yarn and the lappet guide. So, T0 is more than Ts. So, T0 is Ts e to the power mu 1 theta, where theta is the angle of wrap. Relation between tension at the lappet T0 and at the entry point to the traveler in the balloon, it is here. How T0 and Tr are connected? That is connected by this equation. Actually, Tr is a point on the balloon, therefore, Tr is T0 minus half m over square r square. If we shift T0 to the left hand side and bring Tr on the right hand side, then we say T0 is Tr plus half m omega square r square. If I go by the previous slide, so we have seen earlier what, I will just quickly go back so that you remember. T is T0 minus half m omega square r square, where T is the tension at any point on the balloon. So, if I replace T by Tr, where the traveler exists at that point, that means Tr is going to be T0 minus this, and therefore, T0 is going to be Tr plus half m omega square r square. That exactly we have written here. T0 is Tr half omega square r square, where r is the ring radius, Tr is the tension in the balloon length at the ring traveler as shown in the diagram here, m is the mass per unit length of the yarn. From there, now we find out the relationship between winding tension and Tr, relationship between Tr and Tw. So, here also the yarn is going under the traveler. So, there is an angle of wrap. So, the relationship between Tw and Tr is going to be Tw equal to Tr e to the power mu 2 into beta, where mu 2 is the coefficient of friction between yarn and the traveler. So, Tw is more than Tr because I am pulling the yarn. No, Tw is the yarn is traveling towards the bobbin, and therefore, T0 is always more than Ts and Tw will be greater than Tr. So, Tr, from here we can write Tw e to the power mu 2 beta, and the way we want to write it, Tw in terms of Tr or Tr in terms of Tw. Therefore, Tw, these winding tensions we have calculated earlier also, and we have shown it in the previous session that Tw depends upon these parameters. This was what was deduced earlier. Tw is mu mt dr omega square by 2 sin alpha, where mt is the mass of the traveler, alpha is the angle of point, and mu is the coefficient of friction between ring and traveler. So, this is what we have seen it earlier, where the traveler weight comes into the picture and mu is the coefficient of friction between ring and traveler. So, winding tension is very much dependent on the value of mu, the weight of traveler, omega, and the angle of wind, which keeps on changing. The minimum diameter, angle is small, the maximum diameter, angle is more. That means, the denominator part keeps on changing as the ring rail moves up and down. Hence, we can write, if Tr we write it this, we replace the Tw by this. So, we write Tr is going to be mu mt dr omega square by 2 sin alpha. So, just it is the substitution of value of Tw in this equation 5, and we get this. That is what is my Tr. So, Tr and Tw, in Tw replaced by the parameters related to weight of traveler, diameter of ring, and the speed with which the balloon is turning, and the angle of wind. This is the equation, and the last thing is about this relationship between spinning tension. So, if T0 is Tr into Tr plus half omega square r square, this is the equation number 3, we have seen it earlier, and substituting value of Tr, we get now Tr we have seen in the previous slide. So, T0 becomes Tr plus half m omega square r squared is going to be how much? It is going to be dr by 2 whole square, and therefore, T0 is going to be this, and Ts and T0 we have seen it how they are connected Ts is T0 e to the power minus mu 1 theta, and hence Ts, the spinning tension, will be this equation, equation number 9. This is just substitution of the value T0 here, because T0 is T0, we have seen it earlier. Equation number 7, we just put equation number 7 here and multiply it by e to the power minus mu 1 theta. Theta is this angle as shown in the diagram, and mu 1 is the coefficient of friction between the lappet guide and the yarn. So, you see that the spinning tension Ts is related to so many parameters, and therefore, we can write that the various parameters affecting spinning tensions are listed here: traveler weight, ring diameter, traveler rotation speed, linear density of the yarn, coefficient of friction between ring and traveler, between yarn and traveler, between yarn and lappet, angle of wrap around lappet, angle of wrap around traveler, angle of wind. 10 different parameters are there which are affecting the spinning tension, and out of this few parameters are continuously changing, they are not fixed. Like angle of wrap theta is not constant, it is continually changing. Angle of wrap around the traveler beta is also changing, angle of wind alpha is also continually changing. So, though rest of the parameters 1 to 7 remain fixed for a given situation, all these angles keeps on changing, alpha, beta and theta, and therefore, the spinning tension, if we try to measure and record it, we will find that it is continuously fluctuating. Therefore, it is quite, and we all always try to reduce the mu values. How? By always keeping the traveler highly polished, or the lappet guide also should be very much polished, should not be dirty. We have to keep cleaning it time to time. The kind of finish which is given to the traveler, and then the finish which is given to the ring, these are all meant to reduce the values of mu, mu 1 and mu 2, so that we will be able to reduce the tension component in the yarn, and there has to be an optimum combination of all these parameters which will help us to make the spinning stable. Otherwise, lot of breaks will occur, and spinning sometimes may become impossible. So, with this we close this particular session. Thank you.